Welcome back, viewers. Today we have a special announcement coming at you live from Bar Sega, who, with elegance and grace, will briefly explain what it is we're doing today.
Example problems 5.1.
Thank you very much.
Love it. Love it, love it. Okay, on this, we have two ropes tied. Sweet. The tension in each rope is 2.28 newtons, is what they tell me. And we're trying to find the combined force, the magnitude, and the direction of these ropes. Now, quick check here. Which one's the rope? So the solid line. Cool. I know that each of these ropes pull up with 2.28 newtons. Okay. That's the tension in these ropes. Now, if I said, what direction does the left rope pull at? You can probably give me an angle. Maybe you can give me an angle. So let's just try. I want to see what you give me. What direction does the left rope pull at? So if you just tell me 13 degrees, you're on the right track, but I want you to be more specific. 13 degrees, which direction of where? Strange. So I'm okay if, we obviously don't have a compass rose here, but just by convention, what way is up normally? I like north. And although we don't have this, if we put a north, south, east, and west, so think about it. Do you agree it's 13 degrees? We start at north and fall which direction? To the west. So this is 13 degrees 13 degrees west of north is how you would read this. Now, it is entirely up to us. I hate this picture because it drives me crazy. I think they should have done I don't know how I do that. I wish I did. I would have put the angle down here, and I would have just said, check it out, 13 degrees, because I think that makes it a little bit easier. Okay, this rope, imagine I'm pulling, and hey, look at that, I have a rope, and wait, so cool. If I do this exact situation, and I'm like this, and I'm going to lift it, what direction's the weight going to move? So if I pull directly like this, and I'm going to do it here in a second, I'll grab it better, because that's a 1 kilogram mass. What direction will the weight move if I lift it? Just that way? And up, right? Now, as I do that, you guys are right. It did that. It moved to the right and it moved up. What you've just seen are the components of that force. I can pull this direction, but we all understand that this direction that I'm pulling at has some amount that way and some amount that way. Like intuitively, we know that because you've pulled on stuff before. As we look at this picture, my suggestion is let's just think about the components. A single dot diagram or vector diagram, free body diagram, there we go, might be helpful. Here's the swing. And I'm going to draw mine not to scale so I can draw nicer pictures. I know that my tensions are essentially going like this, and I'm going to say tension, is that 1 or 2? I don't care. The force of tension, 1? Okay. I'm going to use A just because it's going to be a little bit easier. And this is the force of tension, B. Everybody okay with saying, hey, look, this picture is the same? All right. Now, I don't care which one we deal with. Again, my angles are going to be awful. Couple options. We can either draw my right triangles up here by doing this and making it a right triangle, which is okay. But if we think bow ties and butterflies, my recommendation would be let's make it that bow tie and butterfly shape. So if you think of the unit circle, remember bow ties and butterflies do this, which means this is the triangle that I would like to look at. That right triangle here is the exact same as this right triangle here. Are you guys okay with that idea? Bow ties and butterflies, do you understand why I like this one more? Okay, and that's all right. Either one will work, but let's check it out. If I use this one, there's a little bit more thought that we have to put into it, but in my mind, it makes it so much easier. So here it is. If this angle is, whoa, I just drew the wrong triangle, right? I went through that whole spiel saying this is the one I want to use, and I drew a different one. This guy. Cool. This was my 13-degree angle right here. What's this angle? 77 degrees? Everybody cool with that? You can get the same answer with 13, just so you know. There's a fancy trig rule. I'm just going to use this one. What's this angle? So here's how I would suggest doing this problem. Do you want to take a super mathy approach or I lied. I'm not even going to give you an option. We're going to take a super mathy approach because we're going to apply the stuff that we did, even though it's not the exact same way your book does it. So here we go. I want to find this vector that's the tension on side A, and I want to write it in component form. This is what I would like to do. So duck face, Instagram, peace signs, here we go. I unfortunately don't remember how to do this. Oh, crap. Man, if only there was something in our notes that said, hey, if you have a vector and here's what it's doing, here's how you find the horizontal and vertical components. I feel like a pirate when I think about it. That's a weird tip, but you might get it when you look at it. So you could, so SOHCAHTOA is involved for sure. And we can do it from a geometry standpoint, but we're going to do it from a simplified standpoint that makes the math a little faster. Given an angle and the magnitude, your resultant can be written in component form. I think it's the last thing we wrote in our notes. R sub x and R sub y, we can find those by doing R times something and R times something. R cos theta and R sine theta. Okay, for this, and there's our SOHCAHTOA, and we can see how this looks from a geometry standpoint instead, but vectors are like the physics tool, just so you're aware. So here we go. What's the magnitude of my force, my resultant? 2.28. So I'm going to say, hey, this is 2.28 times the, gosh, is cosine x or y? X. How do you remember that, just out of curiosity? Like, some of you probably just do. My stupid rule, cosine and sine, c then s, x and y, x then y, c and x. That's my, like, roundabout way. Anyway, 2.28 times the cosine of what? Careful. 77 for this one. Now, here's the deal. If you used 13, because you elected to use this triangle instead, and it's certainly possible, right? We're going to check something here in just a second. I bet the cosine of 77 is the same as the sine of 13. I bet they're the same. Somebody check that for me real quick. One of you guys do the cosine of 77. Sean, do the sine of 13. Cosine of 77 is what? 0.32? 0.22. What's the sine of 13? Check to make sure you're in degrees. Check to make sure you're in degrees. They're the same. One of you was wrong. I don't know who. You're in degrees? And you did the cosine of 77? 0.22495. And you did the sine. Nope, we just need the square. Just the sine of 13. Just double checking. Sorry. Same thing. Okay. So whether you do the sine of 13 or the cosine of 77, we get the same answer, which is, we're going to, like, I'll demonstrate on this other triangle. But cool. There's the x-coordinate of this vector. What's the y-coordinate? .28 times the sine of what angle? 77. Okay. Sean, you already, bless you, you're already on the track here. I'm going to write this vector in its true form. I don't know what 2.28 times the cosine of 77 is, but somebody will be able to tell me that here in a minute when you use it on your calculator. .51. So with trig stuff, my rule, unless specified, we're going to round to 4 decimals. And it feels obnoxious, but 4 decimals is realistically about as far as you need to go to do like the best calculations in our universe. Okay, so with 4 decimals, we get 0.28. Okay, and how about 2.28 times the sine of 77? 2.215. Okay. This is this vector. And I know that this, to get 2.28, it pulls to the right with this many newtons, 0.5128 newtons, and it pulls upward at 2.2215, which makes sense because if I'm pulling at 77 degrees, am I more up or more over? I'll do it from your perspective. This angle right here at 77 degrees, more up or more over? More up, right? It's definitely prioritized there, and I see that on this. I want you guys to do something similar for me. Get me vector, and you might be able to save a little bit of time. I want the vector that represents the tension in B. Now, the only weird part about this, couple different ways that we can think about it. If we use our bow ties and butterflies to make our triangles, and all we're doing when I say that is make the x-axis one of the bottom or top, depending on what quadrant you're in. Looking at this, couple options. Do you know this angle? 77, but there's an issue. Because if I just type in 2.28 cosine of 77, I'm going to get this number. Now, it's close, but there's an issue with this. Can you tell me what the issue is? It should be negative. Now, if you look at the picture, if this is the origin, obviously positive goes that way and negative goes that way. That's the natural choice. If you want to make sure your calculator gets this correct, though, there's a way we can do it. If you don't want to have to think about it, all angles always start from, we measure where to where. We start at some side always. When you think about the unit circle, where's the initial side of your angle? So if I said draw 13 degrees, and I don't even need this, like here's a circle with a coordinate in the middle. If I said draw 13 degrees, it'd be weird for you to start there and do that, right? Even though you could say it's 13 degrees. That's weird to do. What would make it less weird? If you start, so be careful, because you can't just say start at this point and go 13 degrees, because that doesn't mean anything. This is the initial side, right? And then 13 degrees more naturally is here. Okay, here's the thought that we should try to use then. This angle is the big angle that I'm really looking at. If I know this is 13 here and 77, which is all fine, can you tell me what this big angle theta is all the way from here over? So to here would be 180, absolutely. 103, because it's just 90 plus 13 more. Okay, if you type this in and verify for me, if we take 2.28, our magnitude, times the cosine of, what did we just find that actual angle was? 103. I have a sneaking suspicion that you're going to get negative 0.5128. Okay, with that in mind, without typing it in, and if you've already done it, just don't shout this answer. Oh, I hate that too. Cosine of 103. Just kidding, it's sine on the y value. Without plugging it in, any guess on what this is going to give me? $2.2215. It's going to be the same. Do you guys see why that works? Okay, so check it out. This is like 2 seconds of trig. Here's a perfect circle, right? Okay, if I were to take 77 degrees, I'm just going to estimate it. Do you believe it'd be there? Like, just believe it. We'll say it's here. If I go 103 degrees, it'd be here. What do you notice about that y value? They're both positive. Are they the same? There's symmetry on a circle. We are going to use that to our advantage. All right. So looking at this then, we said it was negative 0.5128 and positive still 2.2215. Now I want to stress this technique. It takes a little practice to get used to, and I don't know that you guys did this last year in Algebra 2. Okay. Does it feel okay as we're doing it? As a procedure? Maybe the conceptual, like the deep understanding, shaky? Could you do this again if I give you a different force and a different angle? Cool. So, I need to combine these forces, right? Because that's what I'm trying to find. How could we do that? If I wanted the net force, what are all the forces that we're considering in this problem? So we were never given a mass of this. Because we don't have a mass, I don't think there's any, like we don't have a value to say how hard it pulls down. So there's only two forces at work, right? The tension in rope A and the tension in rope B. Do you guys agree with this statement then? The net force, or the total, all the forces combined is just the force of tension in A plus the force of tension in B. Conceptually, that probably feels okay. Now, because we've done this little bit of work to get these things in a component form, I think we can probably just take these up. And I asked you guys last week when we looked at vectors the first time, I said, hey, you get to write the rules for how vectors work. Here it is, 0.5128, and I'm just plugging in vector A right now, 2.2215, plus negative 0.5128, and 2.2215. How do these add? X to X and Y to Y. I can do half of this in my head. The other part I can't do in my head. 4.4430. Okay, so with this answer, and it may not be completely locked in yet, but we're going to. This is the ending force. If I drew the ending force, I'm going to do it in a big obnoxious color here. We'll use this bright green and we'll make it large. Here's where it starts. What direction does it go? How far to the right? And I'm looking at this just so you know. How far to the right do I go? 0. How far up? So I can't draw it perfectly, but, and I'm going to run out of space, this is what my resultant winds up looking like. It just goes straight up. Now the question, if we read it again, it says, hey, what is the combined force, so that's net force, of the two ropes on this swing? Is there any force left and right? No, because they undid each other, right? Like, it makes sense. Otherwise, this would be, like, tilted and wonky. But we have our answer. The combined force, or the net force, however you want to word it, and we're actually going to write this sentence, the net force, or the resultant, is what direction? Straight up. And that's kind of informal. How many degrees? Yeah, 90. 90 degrees, if you'd rather. Or you can say 0 degrees east of north. Like, there's a bunch of ways you could word this. 90 degrees with how many newtons of force? There's 0 in the x direction. How many in the y direction? And you're right. At this point, though, I am going to round. Like, I won't round until the end. Let's see. We were given 3 significant figures to begin with. So I will use 4.44 newtons. Cool. These problems, this is a very mathematical approach to this problem. It makes it easier, even though it might not sound like it. Some of you inevitably look at this and go, nope, I hate it. I don't want to deal with it. It does not offend me. Anybody feel that way? Like you do not like this problem? For some of you, quick check. If you didn't like this problem, did you like geometry? Interesting. You guys didn't like geometry? I think geometry is super cool. It's all based on a book that was written like 4,000 years ago, which is super, okay, 3,000 years ago, but still cool nonetheless. All right, should we look at a geometric approach if you don't like the fancy math? Okay, so this answer is the way that I would prefer to do it. I'll tell you it is the most efficient way that we know how to do it right now. But if you'd rather do the geometry, let's just check it out. I'm going to look at one triangle and realize that they just counteract each other still. If we don't do bow ties and butterflies, things get weird. Because the triangle that we'd be looking at, and this is going to be drawn wonky, is this one instead, right? This is the other option that we had. Okay, if I asked you to find me this, I'll put a right angle. Nope, that's not a right angle. If I asked you to find me this distance and this distance, could you? Famous Lakota chief that you guys don't really know the story, but what's his name? SOHCAHTOA. Find me those side lengths real quick. Not going to lie, you already have the answer somewhere. But there's something weird that happens when you draw the triangle this direction instead. I'm going to give you a minute. SOHCAHTOA, if you need to see it written out. SOHCAHTOA. Talk with your neighbors. Find me X and Y. And then be clear with your work, because I want to see what the weird part of this is. Looking at this. If you want to find this side right here, what trig function do you have to use? Opposite and hypotenuse. Yeah, I agree with you. And this is where I hate this. We think of cosine and sine as respectively representing x and y, right? If I have to use sine to get this x value all of a sudden, it feels like we're cheating. Because x is supposed to be cosine. Now, because we didn't use bow ties and butterflies, this is how it's going to shake out. But we could do it the same. The sine of what angle are we going from? So the sine of 13 degrees is equal to x over 2.28. Now, notice, and this is that back to that thing that we just mentioned in passing. I know that, what's the complement of 13? 77. Follow-up, what's a complement? They add up to 90. So, when I do this, it drives me crazy because I'm using sine to find an x value, which is okay. The math says we can, but we've just drawn our triangle in a way that makes it weird. Sine of 13 is the exact same thing as the cosine of its complement. I guarantee that this is going to be that 0.5128 number. Guarantee it. Okay, to find this y value, the weird part if we do it this way is what trig function would you use? So cosine, so I get the cosine of 13 degrees is equal to the hypotenuse 2.28 over y. And we get y is equal to 2.28 times the cosine of 13 degrees. Again, this bothers me. It might not bother you. I have a feeling this is going to be what? 2.2215? We get the same numbers, and I can identify these forces. Now, if you like it conceptually with just SOHCAHTOA, cool, do it. But I'm going to tell you, if we have more than these forces acting, do you think it's going to be as simple to do it with just triangles? Not to be rude, or maybe to be a little bit rude. Doesn't matter what you think. It's not as simple. I promise. Cool. Huggins, you had a question or a statement? Mean comment, maybe. Is it because I said it was a mean comment? Okay. All right. Let's do another one like this. I'm going to make up a problem. Yo. It is, but what's adjacent to this 13-degree angle? And what's the hypotenuse? Oh, I had this upside down, you mean, right? Yep, I definitely did. Y over 2.28. Thank you for that. You're right. Cool. If we did that with another triangle now, are we going to get the same values? Specifically, we did it with this triangle just now. If I do it with this triangle, what's the only thing that's going to change? Negative on which one? X. Now, this is sneaking forward a little bit. I don't know that we need to fully do this problem, but can you imagine tug of war? Like you guys have seen tug of war, right? How many people are in tug of war? How many teams, rather? Does there have to be two? You think so? What if, hypothetically, and this is a good idea for pep rally, maybe we have a circle on the floor. And then here we have some fancy knot techniques where we have a group pulling this direction, and a group pulling this direction, and a group pulling this direction, and this direction. Can you imagine four-way tug of war? Where this team wins if they get that knot in the center past this point, and so forth. And so, like, you could do it, right? You could play. Why? Yeah, so you're right. And that's awesome. So if we're looking at this, here's the issue, though. We would probably call this the origin, right at the middle, yeah? If I said, hey, use your triangles to draw this out and figure out who wins, are you going to be able to? So I don't sell yourself short? Maybe. Like, probably. It's just going to take a ton of work, right? However, if and I'm making up numbers here, if I were able to measure these forces and I said, oh, look, it's really 5 and 5, because there it looks like they're pulling at 45 degrees. This is smaller or longer? Whoa, smaller or shorter? What? Longer or shorter? Those are the two words I'm looking for. Shorter, so maybe these guys pull at like -4, roughly. These guys pull at a wonky angle, so maybe it's -6, -2, or -2, -6, I'm sorry. And I'm just making up numbers. And these guys pull at, I don't know, 5, -2? If we can break it down like this, and these are the numbers that we had gotten, can you tell me which direction wins, right or left? To the right, because the overall force in the right direction is how much? So you're right, but give me a number based on what we have on the board. 10. To the right, we're pulling 10 because look, that top group's pulling 5 units to the right, or 5 newtons. The bottom group is pulling 5 newtons to the right, so 10 combined. The left is -4 and -2, so -6. The right side wins. So if we're looking at this, and this is without putting them in, our resultant right now, what's 10 plus -6 if we combine these? Okay, we're going 4 to the right in the end. Okay, now let's look up and down, and the teams need to change. In the upward direction, combined with these two teams, how hard are they pulling? 4 and 5, they're 9, right? 9 upward. How about downward? So -8 down here. Okay, so when you combine those, do you see why? How hard is this group pulling in the downward direction? So 6 down in this group? Yep, and there's our -8. Who wins, up or down? And by how much? Okay, so check this out. When we draw our end vector, and this is our resultant, and we didn't have to do the sign stuff because I didn't give you angles, I just made up nice stuff. This is like we'd already done all the sign stuff. If this is the origin, it goes right 4 and up 1. This is where the ending force wins, right? Which group wins if we say, let's see, 11 graders, 12th graders, 9th graders, and 10th graders? Which class wins? Mazel tov, juniors. You guys win, and I can see that's going to happen. Now, conceptually, this is so much easier. Even if there's a little bit more work, it's easier to get these vectors to get them like this than if I said, hey, just kidding, we're not going to use vectors. We're going to use this. And I know that this pulls at 40 degrees. And this triangle pulls at, I don't know, 13 degrees. And this one pulls at, I don't know, what's that angle? I don't know. Sure. If you had to do all these triangles, this problem gets a lot more convoluted really fast, right? Like it gets, ugh. This is a huge benefit. It just takes practice, which we're going to get like now. And we're going to keep getting practice because vectors make math easy. They make physics easy. How many dimensions are in our world? 3. So it means like anywhere that I'm at, if I wanted to, and this is just kind of a fun thing, we're not doing this math, but I want you to be aware of it. We always work in 2 dimensions, right? But math in 2 dimensions is awesome for flatland, which is 2 dimensions. Does 2-dimensional math work perfectly in 3 dimensions, though? So on a flat piece of paper, 2 coordinates is all you need. What if I want to know this point right here from my finger? Let's say my finger here is the origin. To get to this point, how would you describe how to get to it at the tip of this finger? And it's weird. I have to go up this far, and then I have to turn. So if I go up this far, then I have to turn some angle and go that far. So all of a sudden, there's 3 coordinates. We can do 3-dimensional math with 3-dimensional vectors. 3, 2, 1, hypothetically. It says go 3 in the x direction, 2 in the y, and 1 in the z. Which all that means to us is if we go 3 in the x, here's our origin. I go 1, 2 in the y, and then I have to come out towards us the length of 1. So we get our 3rd dimension. Okay. There's a lot of different theories out there that say that there's more dimensions than we can see, which makes maybe sense, maybe not. I don't know. Can anybody think in 4 dimensions? Can you tell me what a 4-dimensional anything looks like? So it's called a tesseract, and you can see it. It's weird, but we can't really imagine it. But check it out. Don't have to be able to imagine it, because right now this vector's in how many dimensions? 4. Oh my gosh, 4-dimensional math is easy if you use vectors. But check it out. Now we're in 6 or 5 dimensions, and 7 and 8. We can do the math. It still works. Everything's fine in however many dimensions we want to work in. It's just an extension of what we're doing in 2 dimensions. Would you like to take a quick brain break and see a tesseract? Okay, so I can't really show you a true tesseract, but here's the logic behind it because we're just going to see a quick animation. If we take a 3-dimensional figure, and I want to represent it on 2 dimensions, can I just kind of use a shadow? Like if I have a sphere in front of me, that's a 3-dimensional shape, and I take a light and I shine a shadow, it makes my sphere 2 dimensions because it turns it into a circle, right? So a 3-dimensional shape, its shadow is 2 dimensions. Everybody good with that? Okay, if we had a 2-dimensional shape, and this is hard to think about, and we lived in a 1-dimensional world, what would they see if they were looking at this?
They might see a line if they're looking here, but realistically, they would only see a point on it. They would only see one dimension of it. Okay, we're going to expand it. A 4-dimensional object, if you cast its shadow, it should be in how many dimensions? 3. That's the concept. It's incredibly hard to grasp, but let's check it out. I think that's an E, but that's okay. All right, here it is. Here's what happens when you slide a tesseract around. This is a 4-dimensional cube. And it's like, do you guys know who MC Escher is? The weird art that looks like it doesn't work and it really doesn't work, but he draws it well. That's a 4-dimensional cube. It's weird. It's rotating on itself. It's like super hard to think about, super hard to visualize. But the vectors, the math that you do with it, they're not hard. They're just vectors with 4 pieces. While we're here, would you like to see another 4-dimensional shape? What do you want? 4D triangle? I don't know what it's called. Whoa. Hate it, just for the record, so we're going to just use silence. Hey, look, 4th dimension, 5. Does it have meaning anymore? No, not visually anyway. Current theories, maybe 11 is what people have to use to make the current understanding of our universe work. 11 dimensions means nothing when you try to think about it. Mathematically, though, everything works. Cool. Let's do a harder problem, and then we're going to call it there. Or, I lied. No, it's not much harder. All right, you guys are going to help me do the other problem. And then from this, were 11, 12, 13, 14, 15, and 16 doable? Or were they also, like, was your total drive just killed by the first 2?
When you only have one line, how are you supposed to find the components of it?
When you only have one line, which, is that like a specific question on a problem?
Yeah.
Which one?
12 and 13.
Find.
Maybe it's obvious, but I...
No, you're good. So you're looking at like vector k, right?
Yeah.
Okay, so vector k, and this is on problem 11. We're going to do number 10 together here in a second. If here's vector k, and it has a length of -4, right? If this were the origin and you went 4 to the left, what's the x component? How far to the x direction? How far in the y direction?
I don't know.
You do. How far up or down did I have to move just now?
Oh, 0.
That's it.
That's the only...
This is the component vector. So there are 2. Don't, like, be really careful. The x component's -4. The y component is
0.
good. Yep. So there still are 2. 0 instead of nothing. Cool. All right. So I want you guys, as I'm going to struggle with the technology here for a second, I want you guys to look at number 10. And if you haven't done so yet, try to draw me a free body diagram. I promise it helps. I'm going to copy and paste mine. I want you guys to draw a free body diagram for number 10. I'm stuck. Now, this one, we're going to get back into the habit of making our knowns and stuff, but because I'm focusing more on the trig right now than anything else, like I'm being kind of fast and loose with it, just so you guys are aware. I need a box, I think. Okay, so I got to have a box. On my free body diagram, what's that box going to look like? It's a dot. Beautiful. It's a box. So, let's see here. I don't know who is who. Do they specify? Nope. Who's Afua? Left or right? Doesn't matter. Left. Why? And Chrissy. Cool. All right. Now what? We got their letters. I'm good with that. Do they pull on a rope? Now, it's not going to be perfect, but I'm just, like, this picture's just going to simplify. Here's Chrissy, right? She's pulling at 17.7 newtons. And she's pulling at, and I'm going to write the angle right here. That's theta, and I'm going to write this as theta sub Chrissy, so theta sub C, just so I can keep stuff straight. Her angle is 55 degrees. Cool. Over here, we have Afua pulling a little bit harder, so it's going to be a little bit longer of a line. And
or vector rather. And there's a few different ways that we can do this. I like the idea. Say there's Chrissy and here's Afua. I like the angle that they give us because then we don't have to think about the positive or negative. But if you'd rather think about the positive and negative, there's an easier angle that we can go with. Do you want to commit to using this angle here for theta sub Afua, or do you want us to make sure we change positive and negative x and y, x particularly, and make this her angle? Make that her angle? Okay, so I'm fine with that. If this is 120 all the way around, what's this angle? 60 degrees. Cool. All right. Now we're going to have to account for that, just so you know, when we do this stuff, but we'll make sense of it. Any other forces acting on this? Afua pulls that direction, Chrissy pulls that direction. That's theta sub Afua. And their force was what? 20.4 newtons? Cool. Oh my, gravity. Now, you guys are going to hook it up real quick. I'm going to use orange for gravity here. They don't tell us how many newtons of force are pulled down with. But quick review, do we know the mass of the box? And if you know the mass, how do you get to the weight or the force of gravity? Say it again. Mass times gravity. What's gravity? 9.8. Somebody do me a favor. 3.2 kilograms times 9.8 newtons per kilogram will tell me how big this vector is. Can you say that like a lot louder? 31.36 newtons. Now, it's in the downward direction, but I can see that on my free body diagram. Now, just looking at it, who does it appear wins? To me, it looks like gravity wins, right? Because this number's bigger. But if you answered something else, I don't think you're wrong. We're going to do this problem, but we're going to do it so much faster, and I'm going to have you do some stuff for me. I just need the resultant, right? I just need to know what happens when we combine all of these vectors. So here's all we need to do. I need to find my net force acting on this box. And there's 3 different forces acting on it, right? What's the first force, Mickey? I haven't called on you all hour. Give me one of the forces. How would you write it? F. So, good. You could use TA, but I'm fine with just A with this picture. Plus, Kalisha, give me another force acting on this. Afua's force, for sure. YB. Good, I like that one more. Chrissy's force. And there's one more that, instead of adding it, I'm going to claim that it subtracts. Why does gravity subtract? It's downward. Okay, your challenge, quote unquote, for tonight is I want you to find me these vectors in component form, but check it out. I'm going to give you one for free. FA, and you're going to have to calculate this. What's the magnitude of Afua? Good, 20.4 times the cosine, and this is going to have to be negative, remember, because Afua is pulling to the left. What's Afua's angle that we identified? 60 degrees. And then 20.4 times the sine, we don't need to make it negative this time, of 60 degrees. I want you to do the same thing for Chrissy. Find me the 3 vectors in this form. You do not have to write them all down. You could just write the numbers as long as you calculate it. Bring me these component vectors tomorrow and we'll finish your problem. Cool.